Hello everyone, so in this video we are going to talk about another very important analytical technique in surface chemistry, which is the X-ray photoelectron spectroscopy. So normally we call it as XPS. Now let me go through the quick overview of our technique, the principle, and then we can move into the instrumentation. So basically what happens in this technique is that we have a sample, right? Let's say here we have a sample. So this sample contains with different kind of materials, like let's say it has lead, carbon, sulfur, likewise different kind of materials are there. So what we want to analyze is the composition and how much of composition this each material has on our sample surface, right? Basically from experience we can measure the composition. That's the main thing what we are going to look at. So what we are going to do is we are going to send a X-ray, right? We are going to send some X-rays to our sample surface. Now what happens is let's say our carbon, let's take carbon. So carbon has 1s, 2s and 2p. So let's say our one of the electrons on the 1s has taken the energy we have supplied here, so which is, let's denote it as h mu. Okay, due to this energy, right, the electron has absorbed this energy. Now it cannot stay on the 1s because it has lot of energy. Now what has the electron done? It has gone out of its state. So there's this binding energy, right? Binding energy. So if your supplied energy, this h mu, is more than the binding energy, then this electron will definitely go out from your atom. It will release from the surface and it will emit it out. This is what we want, right? This is the thing we want. We want these electrons to come out of the surface and we will catch them using a detector. That's why we are using X-rays. You know, X-rays are very energetic. So these photons are has very high energy. So that energy is pretty much sufficient to pop out these electrons from the whole atomic level. So this electron will come out. So it will go out. The binding energy here. So this is the energy which we are going to supply to the electron, right? So it has to use some amount of this energy to overcome the binding energy, and also there will be another very small energy we denote as psi. This energy is also been reduced from our initial energy because there can be vibrations and those kind of energy reductions, right? So the rest of the energy we can detect it as kinetic energy. So we can denote it as K. Okay, so this is the process. So we are going to introduce energy which is from the X-ray. Our electron will absorb its energy and it will overcome the binding energy and come out of the surface. We will catch the electron using detectors, right? When we catch these electrons, it will have some certain of energy, right? Some amount of energy. This K is that value. K is the energy that it has. Always remember, if you understand this concept correctly, always h mu is always larger than the K. Why? Because this electron has obtained this h mu of energy, right? As an example, let's say we have 500 of amount of energy here. So electron has absorbed 500. It has to spend some amount of energy to overcome this binding energy. So let's say the binding energy is 300. So it has to spend some 300 to overcome this binding energy, and also there are other factors like vibrations, those kind of things the energy will be spent on. So let's spend some 50 also. So the rest 300, 350 and 150 is the rest amount. So that 150 is on the form of kinetic energy. So this K value is 150. H mu is 500. You can see always h mu is larger than your kinetic energy or your detected energy, right? So this is the principle. This is what we are gonna do in X-ray photoelectron spectroscopy. Now, if you have higher amount of particular, let's say particular energy, like this energy, let's say you have very high peak for electrons in 150 energy level, which means there are high level of carbon in here. For the binding energy for 1s electron on carbon is specific. There are no other electron that has this amount of energy rather than carbon. Let's say lead, the electron on lead, let's say 1s electron on lead, it has different kind of binding energy. So the kinetic energy will be changed. So you will have another peak for lead's 1s electron. So you will have another peak. Likewise, you can see many peaks in your output, right? Based on the intensity, we can see what are the compounds that has higher concentrations, what are the compounds that has lower concentrations. This is the principle what we are going to do. Now, before we are moving into the interpretation of this data, right, we are going to talk about the examples also, right? So hang on with me. Let's quickly go with this X-ray source, how we can make this X-ray in order to pop out these electrons. Now this is the X-ray source, right? So we call this at a filament. So the high energy electrons will be released from this filament, and there's a electric gradient. So this gradient, there's an electric field out here. So this will accelerate your electrons, and this electron will hit this surface. We call this surface as X-ray anode. Mostly it's like magnesium oxide. Oh no, sorry, not oxide, just magnesium. It's magnesium. So what happens is, when these electrons get impacted on this surface, right, the X-rays are released. This is the X-ray. The X-ray photons are going to release. So this is a very energy consuming process, right? So you need to cool this down. So we are going to introduce cooling water to make the process much more efficient. So if you are wondering how this impact of these high energy electrons will create X-ray photons, right? But basically what happens is, when this electron get collided with the magnesium surface, right, there will be vacancies in lower energy level of your magnesium, right? Let's say 1s maybe. This electron will collide with electrons on the 1s, and this electron will pop out. So there are vacancies now in the 1s. So what happens is, electrons on the high energy level will come down to the 1s to fill these gaps. When these electrons coming down, they have to release its energy in the form of X-rays. So these energy we can use them to this process. This is how we are going to make this X-ray source, right? We are going to make our X-ray source. And the next thing, now there is a problem in this process. The reason is, when you continuously putting X-rays into your sample, and sample will emit electrons, okay, when electrons are removing from your samples, your sample surface become positive because electrons are removing, right? Sample surface is getting positively charged. You need to avoid that. You cannot make the surface positively charged, because it will change the binding energy. More positive the surface is, more binding energy it gets, right? The positive charge means, like electrons which are negatively charged, they are really hard to overcome the binding energy, because the positive charge will give an extra attraction to the surface. So this will deviate our results. As an example, in this carbon case, I have told you that 300, let's say 300 units are the binding energy, right? 300 units are the binding energy. So our X-ray source has 500 units of energy. So our electron must spend 300 units of energy to overcome the binding energy. Now what happens is, if this continuously happen, your surface getting positively charged. Now the binding energy is not 300, it's like 375, right? It's 375. So you need to consume another extra 75 amount of energy from the initial value. So your final kinetic energy will be changed. Your final kinetic energy will be changed. So let me let me state you the equation for this. So here we have kinetic energy. This must be equal to the total minus binding energy minus the correction factor, right? So here look at this. When your binding energy is getting higher, right? When your binding energy is getting higher, your kinetic energy will be lower. So there is a problem, right? So because we are expecting a particular peak in a specific kinetic energy, because each element's specific, like let's say for carbon, 1s electron of the carbon has specific energy. So a particular peak must be appear on the specific place. But in this case, the peak is deviated because of this positive charge. Okay, now I think you can understand why this positive charge which is forming on our surface is problematic to our results, right? So our scientist has proposed a solution for it. So in the instrument you will have a small part called neutralizer. What this neutralizer is doing is it will spray some low kinetic energy electrons, right? Low energy electrons to the surface. Since our sample is making positive charge, now since electrons are removing from the surface, these low energy electrons will come into the surface and neutralize this positive charge. So that effect from the positive charge will be minimized. That's what we are using the neutralizer for. Now let's move on how we can analyze our particular data. In the XPS, you will see a spectrum. Mostly it's like this. You will see some peaks. Like this you will see some peaks. The axis over here, sorry, I am very bad at line. So okay, let's try to draw it more beautifully. Okay, that's better. The axis over here, it's the binding energy, right? Normally it's like 1000 electron volts to 0 electron volts. Now a small thing you need to remember is that when these electrons are emitting from the samples, our instrument will catch them and calculate the kinetic energy, right? They will calculate the kinetic energy. Based on this kinetic energy, they will determine the binding energy, and they will give you the binding energy for the spectrum, right? The important thing is the instrument reads the kinetic energy, not the binding energy. It reads the kinetic energy and it will change the kinetic energy into the binding energy based on in calculation process. Now when you have that positively charged surface, what happens is, right, when you have that positively charged surface, the electrons have that extra, electrons has to spend some extra energy to overcome this positive charge also, right? So electron has to spend some more energy. So here there is another term is going to be added for the extra energy which the electron has to spend on this positive charge. So which means your kinetic energy will be much lower. So what our instrument thinks is, since our kinetic energy is low, the instrument will think, okay, this electron has relatively higher binding energy. But that's not actually true, right? The binding energy is not high. It's that kinetic energy is reduced because of that extra energy electron has to provide to overcome the positive charge that is generated on our sample. But instrument doesn't know that. He will think that binding energy is high, so it will give the peak relative to this higher binding energy. But that's not actually true. So as an example, let's say you have carbon surface and this is the peak which we have on the carbon 2s electrons, right? Let's say it's on like 300 electron volts, right? Just assumption, right? I can't remember exact value. For now, just hang on with the value. Now what happens is, when you have positively charged surface, kinetic energy is low, so our instrument will think, okay, this electron has higher binding energy. So it will give you an actual peak at around here, like 375 maybe. So this is the peak that instrument shows you, but this is the actual peak that must be there for the carbon 2s electron. So you will not see this peak, you will see this peak. So there's a deviation due to this positively charge. That's the problem we have. Okay, now like that we have several situations where we need some sort of advanced analysis. So we will identify each of them and we will talk about them, how to come up with the solution and how to analyze the particular scenarios. Now another data that we can achieve from this XPS is the concentration of a particular element on the sample surface. So we calculate the concentration, right? Concentration of an element. This is proportional to the peak intensity. Higher the peak's intensity, like in our previous example case, we have the carbon 2s peak, right? So higher the peak, which means higher the carbon concentration on the sample. That's a very basic idea. So this is the key concept which this is how we see the concentration, how we get an idea about the concentrations of our samples. And then our instrument has a technique called energy analyzer, right? What this part doing is it will analyze the emitting electron. It will catch the emitting electron and it will analyze to give you the binding energy. So you will have the term called pass energy, which means that we can determine what is the window that we are looking for, right? So we can make our window narrower, right? We can tell the instrument that we are only focused on this narrow energy gap. Then what happens is it will filter the electrons up to this narrower energy gap. So only the particular electrons with the specific energy, right? If it inside this energy gap, then it will go through. But there's a problem, right? There's a problem, and also there's an advantages also. One thing is you will have very high resolution. Your peaks are accurate, your data are accurate, right? There's the accuracy and higher resolution is there. But on the other hand, you will have low intensity. By limiting your window, by narrowing your window, you are reducing the electron counts. You are reducing the amount of electrons that can come to the detector, which means you will have lower intensity. But the electrons which are coming to the detector, they are very accurate. They are the exact values. So you will have a higher resolution. But in the other case, if you broaden your pass energy, like you will broaden your gap, then you will have high amount of electrons which will come to the detector, which means higher intensity. But not all the electrons are specifically energy, like they are not the exact energy values, right? There are deviation, there are errors, so the resolution is low. That's the problem, right? That's the another thing you need to think about. Now when these electrons comes to the detector and we have our results, right? Each and every element, each and every type of electrons in our elements has specific energy values, right? As an example, let's take carbon, right? If you take carbon, then carbon has different kind of electrons, right? 1s electrons, 2s electrons are there, 2p electrons are there. So 1s electrons have specific amount of binding energy, like yeah, I can't remember exact the value. I think it's around 300 electron volts. This is not exact values, right? It's just assumption. Like 2s electrons, they have another specific energy values. 2p electrons, they have specific energy values. So in this case, in your XPS spectrum, if your sample is purely carbon, then you will only see 3 types of peaks. But actually not, it's 3 types of peak. Actually it's 4 types, because if you remember correctly, the quantum mechanics of these electrons, right? the 2p, we can divide it into two parts, like L plus S and L minus S. So there are this is one type of electron, so this will give you a peak. Another type of electron, this will give you a peak. This is another type of electrons, this will give you a peak, and this will also give you a peak. So total of 4 peaks will be obtained for the carbon analysis. Likewise, each and every element, each and every electrons of each element has specific energies. If you take platinum, right, the 1s electrons of platinum, it may be around 450 electron volts. Likewise, each and every element, each and every electron has specific amount of energy, binding energy. So in your spectrum you will see lot of peaks. Some may be having a higher intensity, which means they have higher concentrations. Some may have very low intensities, which means they have low concentrations, right? So if you are looking for specific element, let's say I am more interested on the carbon, right? I am more interested on carbon. So what I will do is I will look at the data, and I will choose a particular electron, and I will narrow my analysis to that particular energy value. So here 300 electron volts. So I am going to narrow my whole spectrum, whole analysis into this 300 electron volts gap, right? Then I can have higher resolution for the particular peak. Likewise, this is the analysis that we are doing. And another thing you need to know about is energy loss lines. So this is another phenomena that can happen in the XPS. Let me explain, right? Now what happens is, let's say you have carbon, right? Let's say you have carbon, and let's say we are more specific on carbon 2s electron. Now when these electrons are emitted from the surface, some of these electrons, right? Some of these electrons may interact with the other electrons on the surface. So this is basically the surface. So when electrons are emitting, the surface is also consist with atoms, no? So these atoms has an electron density. So these emitting electrons can interact with these other electrons on the surface, or maybe on the environment. There can be interactions. So due to these interactions, there will be another peak. You will see, we call this as hump peak. This is our original peak relative to the carbon 2s electron. This we call as small hump, like you can see, it's a broad peak because of this interaction. It's not a narrow peak, right? It's not a narrow peak. I hope you can understand why this is more narrow and this is more broader, right? Because in this case the interactions are not specific. They can interact with the surface atoms, interact with the environmental electrons, the other electrons, like there are so many interactions. So there is this broadness because the energy deviation has a considerable distribution. But here when you have the 2s electron, like they are the specific electrons, they have specific energy values, so it has narrow peak, right? So that's a small thing which you need to understand. Sorry, I will let's erase this. So this hump over here, we call this hump line as the energy loss line. Always remember, these energy loss lines comes with higher binding energy. So here we have the binding energy. So this energy loss line, don't be fooled with the name, right? So this binding energy is higher compared to 2s electron here. This is the parent peak. This is the parent peak, while this is your energy loss line which has higher binding energy compared to this one, right? Don't be fooled with this because we are interacting with the electrons, right? So there will be higher binding energy considered to the parent peak. And another deviation or another variation that you can observe in the XPS is called X-ray satellites. So these are happening because of your X-ray source, right? So when you have your X-ray source, these X-ray sources are providing you with high energy photons. So sometimes these high energy photons can be focused on more than one specific electrons, and these electron will emitted with a different energy compared to the normal one. So in that scenario, you will see a parent peak. This is the parent peak, and you will see a low energy value. This is called the satellite peak. So let's remember, in this case the satellite peak comes with the low binding energy region compared to the parent one. So the parent peak has higher binding energy compared to the satellite peak. So in this case, input like not specific, I mean the characteristic thing about the X-ray satellites compared to our previous discussion, which is that the small energy loss lines, we have a constant distance between the parent and the satellite peak. In our energy loss line, which we have talked earlier, there is no specific distance because the energy loss lines can happen anywhere closer to the parent peak, right? There's no constant value that this will come at this place, no. But in this case, parent peak and the satellite peak has a constant distance. This distance will wholly depend on your X-ray source. You change your X-ray source, you can change this distance. So sometimes you will see this small satellite peak, so you don't need to be bothered about it. Okay, another instance that you may find with the XPS is called shake-up lines, right? So if you remember originated principle, right? Our electrons are removing from the surface. So if you look at a particular element, these electrons are moving from the low energy states. So there are vacancies and left with excited states ions, right? So now we have excited state ions. So there's a gap between the ground state, here you have the ground state, and these excited states. Now what happens is our emitting electrons, some of the electrons may contribute its energy, right? It will contribute its energy to overcome this particular gap, right? To fill up this gap, they will contribute its energy. So after all, when our electron comes to the detector, it has spent some more energy than the usual. So based on our equation, here you have the kinetic energy, h mu minus binding energy and correction factor, and addition to these things, they have spent another term of energy to this excited state ground state energy gap. Now our kinetic energy is low, right? Kinetic energy is relatively low. What are we? Instrument, right? When you think about the instrument, they don't know anything about it. They just see an electron, they capture the electron and they calculate the kinetic energy. So when the instrument calculates the kinetic energy, it only sees a very low kinetic energy. So instrument thinks, okay, this electron has higher binding energy, but that's not the reality. So what happens is, when in the shake-up lines, apart from your parent line, this is your parent line, you will have another small peak in the high binding energy section, because here instrument read them as high binding energy electrons. So this is the parent peak, and there is also a small peaks in the high binding. Here binding energy is increasing to this direction, so this particular small peak has higher binding energy compared to the parent peak. So this is called the shake-up lines. And finally we have multiplet splitting. Let me take yellow color. We have multiplet splitting. So I will quickly go through with multiplet splitting. So this mainly happen with an electrons which has unpaired electron. Like when the sample hit with the X-ray, right? Here you have the X-ray. Now electrons are to be emitted. So when these emitted electrons are from an unpaired electrons, right? So unpaired electrons are there which the atom. The electrons are emitting from an atom, no? So if those atoms consist with unpaired electrons, then there's a problem. So then there is a possibility for the multiplet splitting. So when you have such atoms, you will see that your original peak is a little bit splitted. Maybe for the two peaks, 3 peaks, or it's just a small hump like this. So I will not go into much more details regarding the multiplex splitting, because it's a really interesting factor, right? There's a lot of analyze which we can do with the multiplex splitting. We can identify specific elements such as, so I will dedicate another specific video for this, unlike, because currently as you can see the video is relatively lengthy and we also need to discuss some small examples also. So I will keep this multiplex splitting topic for another day. For now, let's finish this session with a small example, shall we? So here's the question, right? So here we have an element. It's like this. So I'm going to number these carbons. This is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. What I want you to do is, I want you to assign these numbers for these peaks. So binding energy is increasing on this direction. Let's assume that there are only carbon 2s electrons, right? So there are no other peaks, only carbon peaks are there. So sorry, I will erase one. So one peak is not there. Only 4 peaks are there, right? So I want you to analyze this situation and assign the numbers for each of these peaks. What you need to think about is the environment, right? As you can see, look at this carbon number 1. It's surrounded with fluorine atom. Fluorine are very electronegative and they will pull electrons out from the carbon, which makes the carbon relatively positive, right? So when your electrons are emitting from your carbon, right, this small positive charge will create an extra attraction to your electrons. So this electron will have that extra binding energy. Electron will feel the binding energy is relatively high. So in this case, when it comes to the carbon with 3 fluorine atom, it must have very high binding energy. So compared to the other carbon atoms, this carbon atom has the highest positively charged environment. So this carbon atom will create the highest binding energy for the releasing electrons. So the highest binding energy peak should be for this carbon. And then you need to find what's the next environment. What's the next carbon which has the highest positively charged environment. So these two carbons are pretty much similar. But this carbon over here, it has 2 oxygen atoms binded to it. Oxygens are also electronegative, so they will also pull electrons out from a carbon. So you will see this has relatively positive environment compared to the carbon, since you don't have to consider this one again. So this peak should be for the number 2. Now you have 3 and 4. So 4th carbon has no atoms related to the electronegatively charged. So you can assign this one as the last one. And the 3rd one, which is connected to the oxygen. So oxygen will pull out the electrons from the carbon. So you will see some positively charged environment over here. So this should be here. So likewise, these are the space what we are basically doing. So we will do some advanced questions regarding these analytical methods after we have talked the whole series. For now, I hope you are okay with it. If you have any question, feel free to answer. Feel free to put it on my comment section. I will try my best to answer this question. And also you can contact me from my email. Please try those things. In our next video, we will talk about the AES, which is called Auger Electronic Spectroscopy, one of another very amazing techniques which we will use on surface chemistry.